Hello, chemistry students. Welcome to the start of Chapter 9, Section 1, Using Everyday Equations and Interpreting Chemical Equations. Chapter 9 is titled Stoichiometry, and 9.1 is the arithmetic of equations, which should suggest to you that there's going to be math involved. So you're going to want to have your periodic table, your helper sheet, your polyatomic ions you have memorized, all of those sorts of things, your chemistry toolkit, all handy as we go through the couple sections of Chapter 9 that we're going to talk about. So this one, we start by talking about using everyday equations, and we're going to start with the definition of stoichiometry. Stoichiometry is the calculation of quantities, again, or amounts in chemical reactions. So basically, stoichiometry is going to take and kind of meld together your ability to write and balance a chemical equation that you learned in Chapter 8 and the math involving the mole that you learned in Chapter 7 and put that all together to do stoichiometry. So we're going to use balanced equations and mole, your chemistry toolkit, those conversion factors that have moles in them, and use those to calculate the quantities in chemical reactions. Now, these calculations are actually called stoichiometric calculations. These are calculations involving or using balanced equations. Now, that is why I feel this was really important for us to at least touch on before chemistry ended this trimester, okay? Stoichiometric calculations, for those of you who are going to continue and have to take a college-level chemistry class. In college-level chemistry classes, you will have labs, probably weekly. You'll have a separate time outside your class where you'll meet and have a lab for every week of the semester. Okay? In those labs, you'll typically have to do a lab report, and you'll oftentimes have to do calculations. And the kinds of calculations that you're going to be asked to do oftentimes are going to be these stoichiometric calculations. That's why it was really important to me that we at least touch on these couple sections of Chapter 9 before we end the trimester. Okay? So, again, I want to make sure you've kind of seen it before. I certainly don't expect you to be an expert at it, but at least the fact that you've been introduced to it before. You can think about stoichiometry as sort of a chemist's form of bookkeeping. Okay, so it's how a chemist would figure out how much they've started with, how much they're going to produce. So again, stoichiometry is something that any chemist who's working in industry, that chemical companies are doing all the time, right? Dow Chemical Company, if you order some sort of product that they produce from them and you order 1,000 pounds of it, they don't want to produce 2,000 pounds of it. You've only ordered 1,000 pounds. They can only sell you 1,000 pounds, right? 1,000 pounds of it would be waste, okay? So how do, again, pharmaceutical companies, chemical companies, how do they figure out how much reactants they need to start with to produce the correct amount of product that they're selling that they have an order for? Well, they use stoichiometry. And they use the stoichiometric calculations. So stoichiometry is a chemist's form of bookkeeping. We're going to talk about an example that I actually think many of you are going to have some familiarity with, which is cooking. Okay, so this is kind of, one of your kind of dots there. okay, is a cooking example. Now, since I was at home, I could go find a recipe for my favorite cookies, which are oatmeal raisin cookies. And let me say, as I was looking for a recipe, the first one I came across had chocolate chips in it. What kind of crazy person is going to put chocolate chips in an oatmeal raisin cookie? That's horrible. That ruins the cookies. So I had to do a little looking. This is the recipe from the inside of the Quaker Oats canister. So, and I've made these cookies before. They're very, very good. Okay. So, you'll see that this is a recipe, right? Most of you have done some stoichiometry before if you've done some baking, right? So, let's say that you were trying to butter up Mrs. Kremschreider and you were going to make her some oatmeal raisin cookies and bring them to school and give them to her, hoping that maybe that might give her a little leniency with your grade, okay? So you go to make the cookies, you find this recipe, and you go to make the cookies, and lo and behold, you don't have 2 eggs, right? The recipe here calls for 2 eggs. You have 1 egg, but you don't have 2. Okay? Can you still make the recipe? I hope you know you can, right? All that means is if I only have 1 egg here, what do I have to do to the rest of my ingredients? I have to cut them in half, right? So instead of using a half a cup or a stick of butter, I'm going to use a half a stick. Instead of using 3/4 of a cup of packed brown sugar, I'm going to use half that amount. Instead of half of a cup of granulated sugar, I'm going to use 1/4 of a cup. Okay, so instead of a teaspoon, I'm going to use a half a teaspoon, right? I could take this recipe and I could cut all the ingredients in half if I went and discovered I only had 1 egg. Now, also notice down here, it tells me how many cookies to expect, right? It says I'm supposed to make 4 dozen cookies. Now, 4 dozen cookies is based on the idea that I have 2 eggs. But if I only have 1 egg, should you expect to make 2 dozen cookies? Or sorry, 4 dozen cookies? I hope not. I hope then you realize that you're only going to get 2 dozen cookies, which is plenty for me, by the way, because nobody else in my family likes oatmeal raisin cookies, so I don't even have to share. Okay? So, you've done stoichiometry before when you've taken a recipe and you've adjusted it, right? Sometimes we don't even just do this, right? Sometimes we might, okay, you might need to make cookies because you're a National Honor Society and you're supposed to make cookies for the blood drive. But you're supposed to make a whole lot of them. Maybe you're supposed to make and bring 8 dozen cookies. Now notice, again, this recipe makes 4 dozen. Can I follow this recipe the way it is? No. I have to double the recipe, right? And so to double the recipe, that means that you're going to take all of the ingredients listed here and you're going to use twice as much. Okay? That's stoichiometry. That's the idea of what we're going to be doing with these balanced chemical equations. We're going to be figuring out, if we start with a certain amount of reactant, how much product are we going to produce? If I have this much reactant, how much of this other reactant do I need to react with it? Okay? Because, again, right, if I only have 1 egg, I can't use a half a cup of sugar. I better only use 1/4 cup or my cookies aren't going to turn out correctly, okay? So, again, that's what we're going to be doing in stoichiometry. So, interpreting these chemical equations, okay? Information that you get from a balanced equation. And our balanced equation we're going to look at is nitrogen gas reacts with hydrogen gas to form ammonia gas. I hope that you can pause this video for just a moment and write a balanced chemical equation for this. Now, I will help you a little bit because ammonia, you may not know the formula for. Ammonia is NH3. And remember, we want to leave spaces in front of our chemical formulas for coefficients because we're going to have to balance our chemical equation, right? The key word being here, balanced. We're going to have to write our equation and then balance it. So, again, you can pause this. Nitrogen gas. Remember, nitrogen is part of our Dr. Brinkelhoff, so it's N2. Reacts with is our plus sign. Hydrogen gas, so again, that's part of Dr. Brinkelhoff, so that's going to be H2. To form is our arrow, and ammonia gas as NH3. So now, when I start to look at balancing this, right, I see 2 nitrogens, 1 nitrogen. I also see 2 hydrogens and 3 hydrogens. And when I see 2s and 3s like that, hopefully you sort of remember, hey, I'm going to have to make those 6. So to get 6 hydrogens over here, I'm going to use a coefficient of 2. And to get 6 hydrogens here, I'm going to use a coefficient of 3. So my hydrogens are now balanced, but I have 2 nitrogens. I also have 2 nitrogens on my reactant side, so this is now a correctly balanced chemical equation. So again, okay, really important here when we're doing stoichiometry is that we're always going to have to start with a correctly balanced chemical equation. And to have a correctly balanced chemical equation, that means I have to have my chemical formulas correct, okay, and then I have to add my coefficients. So what information can we get from this balanced chemical equation? Well, one of the pieces of information we can get is we can interpret this balanced equation in terms of representative particles. Now remember, we've talked about representative particles before. This is this idea that if I have a big chunk of some substance, what's that smallest piece I can chop it up into and it still has all the properties of that substance, okay? So we've talked about representative particles before. Typically when we're talking about representative particles, we're going to be talking about either molecules for molecular compounds. Remember, I know it's a molecular compound because it's made of 2 nonmetals. I might be talking about formula units for ionic compounds. Remember, I'm going to know it's an ionic compound because it's made of a metal and a nonmetal, or it has a polyatomic ion. And I may be talking about atoms for elements. Okay, so because we only have these 3 kinds of substances, we have these 3 representative particles. So let's look at this equation, this nitrogen reacting with hydrogen to produce ammonia, okay, and let's interpret this equation in terms of representative particles. Well, these are all molecular compounds. So every single time I talk about representative particles, I'm going to talk about molecules. And when I interpret it this way, my coefficients equal my number of representative particles. So when I interpret this equation, I have 1 molecule of nitrogen, 3 molecules of hydrogen because the coefficient on hydrogen is 3, and I produce 2 molecules of ammonia. Again, it was molecules here because every single time here this substance is a molecular compound. If I had been talking about an ionic compound, so if we had been talking about sodium reacting with chlorine to produce sodium chloride, right? So if we I'll write that one real quick here, right? Sodium reacting with chlorine to produce sodium chloride, right? Then to interpret something like that, because sodium's an element, I would say I have 2 atoms of sodium. Because chlorine is a molecular compound, I'd have 1 molecule of chlorine. And because sodium chloride is an ionic compound, I would produce 2 formula units of sodium chloride. So I still use my coefficients for my number of representative particles, but the representative particle, what I call that representative particle again, depends upon what is the substance I'm talking about. Okay, so one way we can interpret chemical equations and information we can get from our balanced chemical equation is we can interpret it in terms of representative particles. When we do that, our coefficients tell us the number of representative particles. Second way that we can interpret this balanced chemical equation, and again, I just put that balanced chemical equation there again so that you could see it, is we can interpret this in terms of moles. Again, when we interpret this in terms of moles, our coefficients are going to equal the relative numbers of moles. Okay, so we're going to use our coefficients again. So when I look at this equation, because my coefficient on nitrogen is 1, I'm going to say I have 1 mole of nitrogen. Because my coefficient on hydrogen is 3, I'm going to say I have 3 moles of hydrogen. And so 1 mole of nitrogen reacts with 3 moles of hydrogen, okay, to produce, because my coefficient is 2, 2 moles of ammonia. Okay, so that's how I would interpret that. Again, if I just look at that other one we talked about, right? Then interpreting this one, I would have 2 moles of sodium because the coefficient is 2. 1 mole of chlorine because the coefficient is 1 produces 2 moles of sodium chloride because the coefficient is 2. So notice that for both representative particles and moles, it's our coefficients that tell us the relative numbers of relative numbers. Okay, whether that's a representative particle or whether we're talking about moles. The third way that I can interpret this balanced chemical equation is I can talk about it in terms of mass. Okay. And we know, remember, there's a law that balanced chemical equations must follow. So we know that balanced chemical equations must follow the law of conservation of mass. Which is going to mean for us that the mass of the reactants has to equal the mass of the products. So to interpret any chemical equation in terms of mass, there's math required. Okay. So again, remember, notice here, right, there was no math. And back over here too, there was really no math. You're just using your coefficients, okay? So the first time we're seeing any math is when we want to interpret our chemical equation in terms of mass. So again, let's look at this example. I'm not going to do 2 examples for this one. I'm just going to do 1. Okay, let's look at this example and see how we would interpret it then. What would the work look like to kind of prove this? So again, we're still going to use our coefficients to tell us how many moles we're starting with. So we're going to have 1 mole of nitrogen, and we want to change moles to grams, which we have a tool that does that, right? That's molar mass. Again, easy number is 1. And in front of grams, it's our number from our periodic table. Okay. Multiplied by 2 because there are 2 of them. So I'm going to use 28.014. Okay. which means, right, this is pretty easy math, 28.014 grams of nitrogen. Now, how many mole, or what am I going to start with for hydrogen? Well, I'm going to start with my coefficient, that many moles. So I have 3 moles of hydrogen. Again, moles of hydrogen have to go on the bottom, so they'll cross out. Grams of hydrogen is going to go on the top because, again, I'm using molar mass. Okay. I have to do 2 hydrogen. So, again, easy numbers, 1 in front of moles, and 2.0158 for grams. So, times 3, because I have 3 moles, so 6.0474 grams of hydrogen. Okay. Let's look at ammonia then. How many moles of ammonia will I start with? 2, right? Because my coefficient is 2. Again, I'm using that same tool of molar mass. So moles of ammonia have to go in the bottom to cross out. Grams of ammonia are going to go on the top. Easy number is 1 that goes in front of moles. And we get about 17.0307 for grams. Again, how do I get all of those numbers right here? Remember, I'm adding up masses from the periodic table, okay? And in ammonia's case, I'm using 1 nitrogen and 3 hydrogens. So I get a mass of 34.0614 grams of ammonia. Now, I want to prove that law of conservation of mass. So remember, these are my reactants. So when I add these two together, hopefully I get 34. So notice I've proven my law of conservation of mass because the mass of my reactants, the nitrogen and the hydrogen added together, is the mass of my product, which is ammonia. Now, this could be a little bit more complicated on homework because you could have a second product, in which case you'd have to add the masses of the 2 products, okay, to see if you follow the law of conservation of mass. So, again, we can interpret our chemical equation in terms of mass. When we're asked to interpret our chemical equation in terms of mass, there is math required. The last way we can interpret our chemical equation is going to be in terms of volume. If we're going to interpret our chemical equation in terms of volume, we're going to assume we have STP, remember standard temperature and pressure, so that was a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals or 1 atmosphere, okay? Because again, that allows us to know about the moles and volumes of gases. Okay, and again, this is one where there's going to be math required. So if you're asked to interpret a chemical equation in terms of volume, again, there's going to be math required. So again, let's take a look at what that math looks like. Again, we're still using our coefficients for the number of moles that we're going to start with. So we're going to start with 1 mole of nitrogen, and we're looking for whether or not we have a tool on our toolkit that relates moles of nitrogen to liters of nitrogen, which we do. Oops, sorry about that. Liters of nitrogen, which we do, it is molar volume. Again, easy numbers 1, and number in front of liters is 22.4. Okay, so we have 22.4 liters of nitrogen gas that we start with. Okay, so how many moles of hydrogen gas will we start with? Right, we're going to start with 3 moles because our coefficient is 3. Again, we're still using the same molar mass conversion factor, so 1 mole of hydrogen is 22.4 liters of hydrogen gas. Okay. So we have 67.2 liters of hydrogen gas. And how many moles of ammonia gas are we going to have? Right, 2 moles. Again, we're using molar volume, so 1 mole of ammonia gas is 22.4 liters of ammonia gas. Okay. So we get 44.8 liters of ammonia. Notice there is no conservation law involving volume. Okay, so volume is not something that's conserved, so your reactants will not equal your products. Okay, but this is how you would interpret your chemical equation in terms of volume. Okay, so again, 4 pieces of information that we can get from our balanced chemical equation. Okay, we can get representative particles, and to interpret in terms of representative particles, our coefficients tell us the relative numbers. We can interpret in terms of moles, and once again, our coefficients tell us the relative numbers. No math required to interpret a chemical equation in terms of moles or in terms of representative particles. We can interpret our balanced chemical equation in terms of mass, in which case we're going to have math required. We're going to use that molar mass conversion factor, and we're going to follow that law of conservation of mass, which is going to show that our mass of our reactants equals our mass of our products. And lastly, we can interpret our chemical equation in terms of volume. We're going to assume we have STP, and again, we have math required. This time we're going to use that conversion factor of molar volume to figure out our volumes of our gases. So that being said, we kind of just did review our conversion factors, but we'll kind of go over this again. So remember, our mole can be used for 3 things. The first thing it can be used for is for counting. Okay, remember our mole, we're talking about, when we talk about the mole, we're talking about a way to measure matter. And one of the ways we can measure matter is by counting. Okay, so our count conversion factor, our generic one, and you probably don't actually have this one on your toolkit, which is fine, but our generic one is 6.022 times 10 to the 23rd representative particles over 1 mole of substance. Now, I say that you probably don't have that one because what you probably put on your toolkit was these 3 different substances that we have down here, right? One of our substances that we can have is an element. Another one of our substances that we can have is a molecular compound. And the last one of our substances that we can have is an ionic compound. So remember, representative particle, we're talking about that smallest piece. We sort of reviewed this already, right? Our smallest piece of an element is an atom. Our smallest piece of a molecular compound is a molecule. The smallest piece of our ionic compound is that formula unit. In terms of mass, for the mass of all of these, we're going to talk about molar mass. Okay, and we're going to talk about that in just a moment here, kind of review that. So, you didn't probably write this generic one. What you probably wrote for count were 3 specific ones. You wrote one that had 6.022 times 10 to the 23rd atoms over 1 mole of element. You wrote one that was 6.022 times 10 to the 23rd formula units over 1 mole of ionic compound. Oops, my cat wants out. And then you had one more. You had the 6.022 times 10 to the 23rd, okay, molecules over 1 mole of molecular compound. Remember, the power of all of these is I can flip any one of these depending upon where I need the units to be so they'll cross out. So one of the ways that we measure matter is by counting, and we can use the mole for that. And again, these are those 3 conversion factors that should be on your chemistry toolkit for counting. The second way that we measure matter is by mass or weight. Again, this is the conversion factor that kind of has a name, right? This is that molar mass conversion factor. Our molar mass conversion factor, we have some number of grams of substance over 1 mole of the same substance. And remember, this number here comes from adding up the average atomic masses on the periodic table. Right, so if we talk about like calcium nitrate, okay, remember we would talk about the fact we have 1 calcium, we have 2 nitrogens, and we have 6 oxygens, right? And calcium on our periodic table is 40.078. Nitrogen is 14.007. Oxygen is 15.999. Right? Everybody kind of remember doing this? Remember. Now kind of put it right now, right? You're not required to show this work. Okay, I'm just showing it here to remind everyone, okay, how we get these numbers that we put in there when we're calculating molar masses. Remember, to calculate molar mass, okay, we must have our chemical formula correct. Okay, if our chemical formula is wrong, we're not going to have the correct molar mass. So again, this is 40.078. This is going to be 28. This is 95. Okay, we add all of those together. Okay. That's our molar mass. Okay, so this is the number right here that we would plug in right here if we were talking about calcium nitrate. Okay, so again, this is one of the tools that's on your toolkit. The last way we have for measuring matter is by using volume. And again, we have a tool for this one, okay, that has a name. This one's name is molar volume. Remember, to use molar volume, we must have the conditions of STP, standard temperature and pressure. So we have to be at a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals or 1 atmosphere. Our tool for this one is 22.4 liters of gas over 1 mole of gas. And when you wrote it on your chemistry toolkit, you probably wrote at STP with it so you would remember. Again, remember the power of molar mass is that I can flip these units depending upon where I need them to be, and the same thing is true here. Okay, so that is your conversion factor review. That brings us to your homework, which is on page 241, questions 6 through 8. Show all of your work if you're doing math problems. Other than, right, you don't have to show calculating your molar mass. You can if you'd like, but that's not required. Have a great day. Talk to you tomorrow.